I wonder if you can speak to the bureaucracy, the political battles, the scientific battles for time on the James Webb Telescope. Is there there must be a fascinating it's process of scheduling that all scientists are trying to collaborate and figure out what the most important problems are, and there's an interesting network of interfering scientific experiments probably they have to somehow optimize over.
It's a really difficult process. I don't envy the TAC that are going to have to make this decision. We call it the TAC, the Time Allocation Committee, that make this decision. And I've served on these before, and it's very difficult. I mean, typically for Hubble, we were seeing at least 10, sometimes 20 times the number of proposals for telescope time versus available telescope time. For JWST, there has been one call already that has gone out. We called it cycle 1, and that was oversubscribed by, I think, something like 6-1, 7-1. And the cycle 2, which has just been announced fairly recently, and the deadline is actually the end of this month. So my team are totally laser focused on writing our proposals right now. That is expected to be much more competitive, probably more comparable to what Hubble saw. And so it's hard.
More competitive than the cycle 1, you said already? Because that's already
more
super
competitive than the first cycle. So I said the first cycle of James Webb was about 6-1, and this will probably be more like 20-1, I would expect.
So these are all proposals by scientists and so on, and it's not like you can schedule at any time. Because if you're looking for transit times,
you have a time critical element.
Yes, time critical element, and they're conflicting in non-obvious ways because the frequency is different, the duration is different.
Right.
There's probably computational needs that are different. There's the type of sensors, the direction pointing, all that.
Yeah, it's hard, and there are certain programs like doing a deep field study where you just more or less point the telescope, and that's pretty open. I mean, you're just accumulating photons. You can just point at that patch of the sky whenever the telescope is not doing anything else, and just get to your month. Let's say a month of integration time is your goal over the lifetime of JWST. So that's maybe a little bit easier to schedule. It's harder, especially for us looking at cool worlds, because as I said earlier, these planets transit very infrequently. Mm-hmm. So we have to wait. If you're looking at the Earth transiting the sun, an alien watching us, they would only get one opportunity per year to do that observation. The transit lasts for about 12 hours. And so if they don't get that time, it's hard. That's it. If it conflicted with another proposal that wants to use another time critical element, it's much easier for planets like these hot planets or these close-in planets because they transit so frequently. There's maybe 100 opportunities. And so then the TAC can say, okay, they want 10 transits. There's 100 opportunities here. It's easier for us to give them time. We're almost in the worst case scenario. We're proposing to look for exomoons around 2 cool planets. Mm-hmm. And so we really only have one bite of the cherry for each one. And so our sales pitch has been that these are extremely precious events. And more importantly, JWST is the only telescope, the only machine humanity has ever constructed, which is capable of finding moons akin to the moons in our solar system. Kepler can't do it, even Hubble can't do it. JWST is the first one. And so there is a new window to the universe because we know these moons exist. They're all over the place in the solar system. You have the moon, you have Io, Callisto, Europa, Ganymede, Titan. Lots of moons are fairly similar size, sort of 30% the size of the Earth. And this telescope is the first one that can find them. And so we're very excited about the profound implications of ultimately solving this journey we're on in astronomy, which is to understand our uniqueness. We want to understand how common is the solar system. Are we the architecture that frequently emerges naturally, or is there something special about what happened here?
I think this is not the worst case. It's the best case. It's obvious. It's super rare. So you have to I love scheduling from a computer science perspective. That's my background. So algorithmically, to solve a schedule problem, I would schedule the rarest things first. Yep. And obviously, this is the JWST is the first thing that can actually detect a cool world. So this is a big new thing. You can show off that new thing. It happens rarely. Schedule it first. It's perfect.
You should be in the TAC. This is perfect.
I will. I'll file my application after we're done with this. I this part of me is the OCD. Part of me is the computational aspect. I love scheduling computing device because you have that kind of scheduling on supercomputers. On that scheduling problem is fascinating. How do you prioritize computation? How do you prioritize science, data collection, sample collection, all that kind of stuff? It's actually kind of is kind of fascinating because data in ways you expect and don't expect will unlock a lot of solutions to some fascinating mysteries. And so collecting the data and doing so in a way that maximizes the possibility of discovery is really interesting, like from a computational perspective.
I agree. There's a real satisfaction in extracting the maximum science per unit time
exactly.
out of your telescope. And that's the TAC's job. But the TAC are not machines. They're not a piece of computer code. They will make their selections based off human judgment. And a lot of the telescope, certainly within the field of exoplanets, because there's different fields of astronomy, but within the field of exoplanets, I think a good expectation is that most of the telescope time that James Webb have will go towards atmospheric retrieval, which is sort of alluded to earlier, like detecting molecules in the atmospheres, not biosignatures, because as I said, it's really not designed to do that. It's pushing JWST probably too far to expect it to do that. But it could detect, for example, a carbon dioxide rich atmosphere on TRAPPIST-1e. That's not a biosignature, but you could prove it's like a Venus in that case, or maybe like a Mars in that case. Like both those have carbon dioxide rich atmospheres. Doesn't prove or disprove the existence of life either way, but it is our first characterization of the nature of those atmospheres. Maybe we can even tell the pressure level and the temperature of those atmospheres. So that's very exciting. But we are competing with that, and that I think that science is completely mind-blowing and fantastic. We have a completely different objective, which is in our case to try and look for the first evidence of these small moons around these planets, potentially even moons which could be habitable, of course. So I think it's a very exciting goal, but a TAC has to make a human judgment essentially about which science are they most excited by, which one has the highest promise of return, the most highest chance of return. And so that's hard because if you look at a planetary atmosphere, well, most of the time the planet has an atmosphere already. And so there's almost a guaranteed success that you're going to learn something about the atmosphere by pointing JWST at it. Whereas in our case, there's a harder sell. We are looking for something that we do not know for sure exists yet or not. And so we are pushing the telescope to do something which is inherently more risky.
Yeah, but the existence, if shown, already gives a deep lesson about what's out there in the universe. But that means that other stars have similar types of variety as we have in our solar system. They have an Io, they have a Europa, and so on, which means like there's a lot of possibility for icy planets, for water, for planets that enable planets and moons. That's super exciting because that means everywhere through our galaxy and beyond, there is just innumerable possibility for weird creatures.
I agree.
Life forms.
You don't have to convince me. I mean, NASA has been on this quest for a long time, and it's sometimes called Eta Earth. It's the frequency of Earth-like, usually they say planets in the universe. How common are planets similar to our Earth in terms of ultimately, we'd like to know everything about these planets in terms of the amount of water they have, how much atmosphere they have. But for now, it's kind of focused just on the size and the distance from the star, essentially. How often do you get similar conditions to that? That was Kepler's primary mission, and it really just kind of flirted with the answer. It didn't quite get to a definitive answer. But I always say, look, if we're looking, if that's our primary goal, to look for Earth-like, I would say, worlds, then moons has to be a part of that, because we know that Earth-like, from the Kepler data, the preliminary result is that Earth-like planets around sun-like stars is not an inevitable outcome. It seems to be something like a 1 to 10% outcome. So it's not particularly inevitable that happens. But we do often see about half of all sun-like stars have either a mini Neptune, a Neptune, or a Jupiter in the habitable zone of their stars. That's a very, very common occurrence that we see. Yet we have no idea how often they have moons around them, which could also be habitable. And so there may very well be, if even 1 in 5 of them has an Earth-like moon or even a Mars-like moon around them, then there would be more habitable real estate in terms of exomoons than exoplanets in the universe.
So you can essentially 2x, 3x, 5x, maybe 10x the number of habitable worlds out there in the universe. Our current estimate for like the Drake equation.
Absolutely. Yeah.
So this is one way to increase the confidence and increase the value of that parameter.
And just know where to look. I mean, we we would like to know, where should we listen for technosignatures? Where should we be looking for biosignatures? And not only that, but what role does the moon have in terms of its influence on the planet? We talked about these directly imaged telescopes earlier, these missions that want to take a photo, to quote Carl Sagan, the pale blue dot of our planet, but the pale blue dot of an exoplanet. And that's the dream, to one day capture that. But as impressive as the resolution is that we are planning and conspiring to design for the future generation telescopes to achieve that, even those telescopes will not have the capability of resolving the Earth and the moon within that. It'll be a pale blue dot pixel, but the moon's grayness will be intermixed with that pixel. And so this is a big problem, because one of the ways that we are claiming to look for life in the universe is a chemical disequilibrium. So you see two molecules that just shouldn't be there. They normally react with each other, or even one molecule that's just too reactive to be hanging around the atmosphere by itself. So if you had oxygen and methane hanging out together, those would normally react fairly easily. And so if you detected those two molecules in your pale blue dot spectra, you'd be like, okay, we have evidence for life. Something's metabolizing on this planet. However, the challenge here is, what if that moon was Titan? Titan has a methane-rich atmosphere. And what if the pale blue dot was in fact a planet devoid of life, but it had oxygen because of water undergoing this photolysis reaction, splitting into oxygen and hydrogen separately? So then you have all of the hallmarks of what we would claim to be life, but all along you were tricked. It was just a moon that was deceiving you. And so we're never going to, I would claim, really understand or complete this quest of looking for life, biosignatures in the universe, unless we have a deep knowledge of the prevalence and role that moons have. They may even affect the habitability of the planets themselves. Of course, our own moon is freakishly large. By mass ratio, it's the largest moon in the solar system. It's a 1% mass moon. If you look at Jupiter's moons, they're like 10 to the power minus 4, much smaller. And so our own moon seems to stabilize the obliquity of our planet. It gives rise to tides. Especially early on when the moon was closer, those tides would have covered entire continents. And those rock pools that would have been scattered across the entire plateau may have been the origin of life on our planet. The moon forming impact may have stripped a significant fraction of lithosphere off the Earth, which without it, plate tectonics may not have been possible. It would have had a stagnant lid because there was just too much lithosphere stuck on the top of the planet. And so there are speculative reasons, but intriguing reasons as to why a large moon may be not just important, but central to the question of having the conditions necessary for life. So moons can be habitable in their own right, but they can also play a significant influence on the habitability of the planets they orbit. And further, they will surely interfere with our attempts to detect life remotely from afar.